Um, Thank you very much. I'm thrilled to be here. I want to express my thankfulness to the academic board of this symposium for getting me involved. I know it's been a long day, and you all guys want to head back to your places to watch the game. Please stay here. I'll try to give a straightforward lecture so you can enjoy it. I was invited to talk about my experience on high altitude environments. I've been working in places where the lack of oxygen is the norm for a while. My interest lies in the idea that climate change will bring a significant climatic stress to high altitude environments, especially to those ones located in the tropical Andes. So the talk is titled uh, Assessing the Vulnerability of Tropical High Altitude Environments to Changes in Climatic Conditions, to Climatic Forcing, and also to the rapid changes due to land use change and land cover change. I work for the International Research Institute for Climate and Society at Columbia University in the city of New York, and I also teach classes here at a place called a private university called Escuela de Ingeniería de Antioquia, where I'm involved as a faculty professor in the environmental engineering program. Um, my idea is to discuss with you why tropical Andes, why they are so important in terms of their environmental goods and services, and also discuss the set of priority or conservation efforts that need to be prioritized over the years to come due to these changes in climatic conditions. As you can see, global warming has been on the radar of policymakers for a while. Over the past 3 decades, there has been an increasing interest of the stakeholders to make better decisions, climate-informed decisions on how to preserve the different environments. Well, high altitude environments, as you can see on this beautiful plot, became a priority in the latest communications submitted to the United Nations Framework Convention on Climate Change. 5 out of 12 South American countries decided to declare high altitude environments as one of the priority sectors. Why high altitude environments? Well, because they are one of the top biodiversity hotspots on Earth. They have multiple species that are endemic to these environments, which means they cannot be found anywhere on the planet. They provide valuable environmental goods and services, and at the same time, they're under a significant climatic stress due to ongoing changes in climatic conditions. Um, the problem is that South America is the continent with the highest extinction risks rates due to climatic change. We think that due to changes in climatic conditions, all these different species, not only flora species, but also fauna species, will be at stake due to these changes in climatic conditions. At the same time, as you can imagine, forest loss in South America has already surpassed the global rate of disruption of our ecosystems, leading to a significant decrease in the extent of our priority areas. As you can imagine, Colombia, for instance, is one of the countries that has been named as the mega diverse environment, but we're losing that diversity at a significantly high rate. The problem is that climate change is not walking alone, it's walking hand in hand with ongoing disruptions, mostly driven by anthropic disturbances. Climate change and land use change are synergistically driving these ongoing disruptions in these environments. So the idea was to try to propose a project in which we could estimate both ongoing changes in climatic conditions, expected changes in climatic conditions, and expected changes in the land use and land cover change for different time periods into the future. And the idea was to produce such information at a local scale. The idea is that continental scale, regional scale are not good enough for making decisions for this case, for priorities in terms of conservation of these different environments. So the idea is to use the information, produce the set of information that the decision makers need at a local scale to make better decisions in terms of these conservation efforts. We decided to run a very simple project in which we implement a so-called uh, severity index. This one was proposed by NatureServe about 6-7 years ago. It was proposed for the, as you can imagine, North American context, but we decided to create an Andean version of the NatureServe Vulnerability Index. The version that you have in front on this slide has a couple of components. One of them is the climate exposure. The other one is, as you can imagine, the sensitivity of different species to ongoing changes in climatic conditions. So we need to quantify these two different components and merge them in such a way that we can come up with a list of potential scores, indices scores, that you can, with them, make priorities or propose a set of priorities for the conservation of these different species. For doing the first part, for quantifying climate exposure, we propose the analysis of the windows of interest that you see on the slide. The idea was use the available techniques to reconstruct the past, which means to try to, using proxies or using, in our case, the tree ring width, try to, with that, reconstruct what has been the past over the past, if possible, 150 years, and try to bring that information into the present, compare it with what's going on in the field. That means processing on the ground truth data, which is what we call observational or instrumental periods on this slide. The idea is to also implement the simulation outputs of several AGCMs, atmospheric general circulation models, or regional circulation models, and compare their simulation outputs, retrospective simulation outputs, with the on-the-ground climatic conditions. Since, as you can imagine, less than 2% of the hydrometeorological network, or the number of weather stations that we have in our hydrometeorological networks, are installed in altitudes above 2,800 meters above sea level, we decided to, well, we need to instrument the region. We need to deploy a set of weather stations to fill in the gaps of the hydrometeorological networks. That means instrumenting the places. And finally, we needed to run the models into the future to try to analyze the prospective simulation outputs and see what is likely to happen in the years to come. And for doing so, we considered two windows of interest. One is the short term. That means the 2011 to 2030 window period compared to the historical climatic conditions. And the other one is the medium term, the 2046 to 2065 window period. So that's the timeline that you have on the slide. For doing the analysis of GCMs, we follow specific steps like the ones you see on this graph. As I mentioned a couple of minutes ago, we process the simulation outputs of the different models, and we quantified with them key climatic variables, such as, in this case, the change in humidity index, which is the ratio of actual evapotranspiration to potential evapotranspiration. We decided to implement 5 well-known dynamical models, GCMs. They are well known because of the fact that they show really good skill levels for the case of the tropical Andes. One of them, you see here on this graph, is the CCM3 version 6. That's the retrospective version of the Earth system model run at NCAR in the US. The other one is the model proposed by the Center of Oceanic Land Atmosphere Interactions of the US government. The other one is the ECAN 4.5 model, the equivalent Earth system model proposed by the Max Planck Institute. Another one is the Geofluid Dynamics Lab model that is run at Princeton University. As you can see on these different panels, the idea was to compare the grid points of the different models with high resolution digital elevation model to try to define the highest points of the different grid points in a given spatial domain that coincide with the highest peaks of the Andes Cordillera. In other words, the idea was to define the systemic axis of the Andes Cordillera, which is highlighted here on these graphs with the pink grid points. Just to show you the outputs of one of these models, for the case of ECAM 4.5, this is what we got. Let me slow down a little bit here. On the left panel, you have the systemic axis of the Andes Cordillera, represented by the grid points of the ECAM 4.5 that capture the highest points of the Cordillera. And on the right panel, you have on the x-axis the pressure level, which means to the left you'll see sea level, to the right you see the tropopause, and along the y-axis you have, of course, the different latitudes. So the systemic axis extends from the border region between Venezuela and Colombia and goes all the way down to the border region between Argentina and Chile. With these black solid triangles, we are representing the average altitude of the grid point at a given latitude, and with the black crosses, we try to represent here the highest altitude of the grid point at the same latitude. In other words, between these two different icons, between the black solid triangles and the black solid crosses, you have all the different mountain ecosystems that you have along the main axis of the Andes Cordillera. Just to give you an idea, we decided to run the project in three different places. One in Los Nevados Natural Park here in Colombia, right in the heart of the Andean region. The other one in the border region between Colombia and Ecuador, and the other one in the transboundary region between Peru and Bolivia. In color scale, I'm plotting the rates of change, the amount of change in mean annual temperatures over the historical period 1950 to 2010. So in blue, you have the trends that are statistically significant and that exhibit a rate of about 0.05 to 0.15 degrees C per decade. And in red, you have those rates that are statistically significant and that show rates of change of about 0.3 to 0.4 degrees C per decade. As you can see, the highest rates of increase are taking place in the upper levels of the tropical belt, 15 degrees latitude south to 15 degrees latitude north. And by upper levels, I mean altitudes above 400 to 600 millibars. So in more or less 7,000 millibars above, extending all the way up to the tropopause. If you fix yourself at a constant latitude, for instance, if you place yourself here in Los Nevados at this latitude, the rate of change in lower levels is of about 0.16 to 0.18 degrees C per decade. But in the upper levels, up here, where the Paramo environments are located, you get 1.8, 2.4 times what you see in the lowlands. So that means, as you can guess right now, that the tropical belt is warming up pretty fast in its upper levels. And so that's a big issue, not only because of the fact that it affects several circulation patterns, but also because it's a direct threat to the integrity of high-altitude environments. This is driven by many things. One is the change in the environmental substrate due to the adjustment of the atmosphere to the ongoing radiative imbalance. The other effect is the idea that El Nino is playing a significant role, as you can see on these graphs, of the first EOF modes of ambient temperatures on top for different months, focus on a single month along the main axis of the Andes Cordillera. Focus on this specific cluster of grid boxes located above 400 millibars and in the 15 degrees latitude south to 15 degrees latitude north, which means that is walking hand in hand, is almost at the same pace as the observed changes in sea surface temperature anomalies in the tropical basin. Um, in the future, this is what is likely to get. This graph shows, imagine that you have all these different grid points of the tropical Andes. You take all of them and you shake them, and then you put them in a single box, and then you do a frequency histogram to see what you would likely expect to see in the years to come. The blue bars represent the prospective simulation outputs of the Earth system models of the Max Planck Institute for the full context of the tropical Andes. As you can see, it shows expected temperature anomaly of about zero 0.5 to about 2 degrees C for the medium term, and for the this is 4.5 watts per square meter radiative imbalance in the years to come. And in blue, in purple, in yellow, and in orange, you have the same simulation outputs for the CCM4 NCAR model, for the Goddard Institute for Space Studies of the NASA model, and the CM3 of the GFDL model. You see that different prospective simulation outputs, broad spectrum of potential temperature anomalies, which gives us an idea of the uncertainty involved in these projections. And at the same time, you see here the what we call the equally weighted multimodal ensemble, putting all the models in the same box and assigning to them the same weighting factor. With that, unfortunately, we're expecting to see temperature anomalies along the full extent of the Andes caldera that are likely to cross the 2 degrees dangerous climate change threshold, which is, as you can imagine, not good news for our sites. We run this project at a very local scale, trying to downscale all the different simulation outputs into binational specific experimental areas. One of them, as I mentioned, is on the left, is the transboundary region between Colombia and Ecuador. And in this region, we have about 5 to 7 key ecosystems according to the classification of the Comunidad Andina and Naciones. And on the right, you have the different ecosystems, about 15 to 16, which means in total we are evaluating about 22 key ecosystems for the full extent of the tropical Andes. In this case, 15 or 16 for the transboundary region between Bolivia and Peru. And the idea was to try to come up with the projections for any of these specific sites. This is a very simple graph in which we see everything we've came up with. That includes the past, reconstructing the changes in environmental conditions, the observed data depicted by the red solid line, the simulation outputs depicted by the blue solid line, the prospective simulation outputs for both the short term and the medium term. And as you can imagine, not good news again. We are likely to see changes in mean annual temperatures that exceed the 1.5 to 1.7 degrees C threshold, which has been the maximum year-to-year change in mean annual temperatures in the Andes. The idea was to, I'm doing okay with the time, no? I have 1 minute. Okay, I'm almost done. Um, the idea is quite simple. We compared. Can I get 2 minutes, perhaps? No? Okay. Um, the idea was to quantify for different species the extent of a given species that lies within different severity intervals. The most severe intervals is when you cross the 2 degrees, the dangerous climate change threshold. The least severe, interval is when you're about to cross the threshold. So you quantify the amount, the extent, or the proportion of a given spatial distribution of a given species that lies within that system. And based on the different species that you have, you can assess how many of them are likely to have their spatial distributions within the most severe intervals. And we did that for about 2,500 species divided into 3 taxonomic groups: birds, um, dung beetles, and plants. And for the case of the northern Andes, this is what we get. You see that most of these species, about just to give you an idea, about 60% of the species of birds analyzed in this study are crossing the threshold of 2 degrees C, which means they're likely to be exposed to dangerous climate change stress. The problem is that they've been exposed to land use cover as well. So the problem of destroying habitats, fragmenting the environment, and at the same time creating the lack of connectivities between or connectiveness between these different environments is what is driving the loss of the extent of these habitats. So it's not only the increase in temperature, but also the lack of proper habitats for their resolution, for their uh, proper establishment. So this is what we can provide to stakeholders and to policymakers. These are the set of maps that we can produce in which we show them which are the key ecosystems that should be the focus of priority conservations actions or conservation efforts. In our case, for instance, for the case of the Northern Andes, there's the paramount, the urgent need to preserve the foothills, the cloud forests or alto Andean forests that are located on the different flanks of the Cordilleras due to changes in climatic conditions and also to land use change. If you want to work with us, just let us know. Let us know. You can get in touch with us via any of the social platforms that you see online, or just send us an email. Thank you. I was not expecting a question from you, but shoot.
Okay. Well, I really enjoy your talk. Um, I have a question. These GCM generally don't tend to be more uncertain over the mountain area, complex terrain,
Absolutely.
and in large part because I think the rainfall influence temperature. And you did show that very nicely. Different model has very different projection. So when you assess the risk, um, how do you uh, use these uncertainty information?
Good question. Well, first of all, I have to say that for the case of rainfall, we're doing a pretty bad job. Absolutely. And if I want to be exposed to high risk in a lecture like this, I would plot the projected anomalies in rainfall amounts, in annual rainfall amounts, because for the case of the set of models that we implemented, in some cases you get increases in rainfall amount, in other cases you get exactly the opposite. So it's like having this broad spectrum of potential projections. That's a big problem. So temperature, we're doing more or less well. Okay, we get the equally weighted multimodal ensemble, and in some cases, when we get on the ground weather conditions actual data, we assign weighting factors in such a way that we can have a differential weighting scheme, in such a way that we can produce a better ensemble of models for on the ground conditions. Once we get that, then we play with the different changes, with the different severity intervals. So we provide to the policymakers the idea that, yes, this is what you are likely to expect in this specific region, but within this confidence interval. That's the way we do it. But you were right, we're doing pretty bad with rainfall, absolutely bad, and we need help.